try sometimes.
Okay, we're talking about friction today. All right, so far in this class, we have ignored friction. We've been like, oh, this frictionless surface, or like, we're going to neglect friction in this example, okay? So today we stop lying about friction, all right? I know, we've been lying about friction, okay? Now, there's a few types of friction. There's air resistance, okay, we can talk about. We're not talking about that today. We don't really talk about that until AP Physics. Okay, today we are specifically talking about sliding friction. Okay, there's a bear. He's sliding, having fun. Okay, baseball. All right, any surface sliding across another surface, all right, applies to what we're talking about today. Okay, and we're talking about solids. All right, so here's what we want to be able to do. What variables affect how much friction there is present? Okay, what kind of things can we change, and that will change how many newtons of friction? We should mention that friction is a what?
Force.
It's a force, that's right. Okay, so it's measured in newtons. All right, we're going to be able to measure it. We're going to get an equation, new equation today. You guys excited? Okay. All right, so we're going to get an equation. All right, and now we're going to be able to actually deal with friction. Okay, no more lying about friction. It's there. All right, we're going to be able to deal with it. Okay. All right, we will start with a myth busters.
Welcome back. Here's where we stand so far. Jamie and I got word that interleaving the pages of 2 phone books yielded something incredibly strong.
Does this remind you of when you used to count money for the mob?
I was a hitman. I wasn't a money counter.
So we did it, and we tugged on them. We couldn't separate them. We got 10 friends together. They couldn't separate them. We got 2 cars, and still, those phone books wouldn't be separated. But we're not going to leave it there. We went out and found a couple of tanks. Behind me is 30 tons of military steel, 650 horsepower. Are they going to separate the phone books? At this point, I have no idea. But I do know that something is going to happen.
I was trying to make a phone call. That's all I wanted to do.
Okay, go ahead, full slack.
With the lightest of touches on the throttle, the tanks ease delicately apart. The careful positioning not reflected by the force gauge needle.
That's 1,000 pounds of force so far.
With the slack taken up, Jamie signals the start. 30 tons of mighty military machines slowly begin to move in opposite directions. And the force gauge climbs quickly. But the courageous phone books, you couldn't call them yellow, hang on for all they're worth.
There. Separated, it worked.
Okay, so what force was holding the phone books together? Friction. All right. All right, now we take a couple sheets of paper, like so, and we do that, all right? Okay, there's a little force of friction, okay, but we do that thousands of times, all right? I once had my aides do that, all right? We don't have those phone books anymore, but they sat there and they put the phone books together, okay? And you're multiplying this force by thousands, all right? Okay, then what else is happening? So we got this going on. Okay, as we pull them, what are those phone books gonna do? That's right, they're gonna squeeze those pages together, okay? All right, friction multiplied by a lot. Okay, so friction actually only depends on 2 things. Okay, we're going to make some guesses here in a second on what those 2 things are. Okay, but what do you guys think affects the value, the amount of newtons that friction's going to be based on the situation? Okay, just throw stuff out. I'll write it on the board. Okay, what do we got?
Like surface area?
Okay, surface area.
Like thickness of the object.
Okay. What's that? Mass. Keep going, they're just guesses, ideas. Okay, how fast we're pulling it? Nice, Dimitri. Gravity. Okay. Any other ideas? Okay, how about like if I'm pulling like this wood block versus like this metal thing? What's that?
Could be like material it's made out of.
Okay, the applied force, material it's made out of. Okay, so we'll just say FA, force applied, then the material. Okay, all right, any other guesses? Okay, it turns out there's really only two things that friction depends on, only two variables. Okay, all right, we got a big old list here. Which ones actually matter? Okay, let's check it out. All right, the first thing that matters for sliding friction is the normal force. That's why we learned normal force last time with those super exciting diagrams of boxes sitting on tables. Okay, we remember that? All right, that gets us so we can learn about friction. Okay, so force normal. All right, we didn't even have that on our list up here. Okay, but if I've got this block sitting here, all right, maybe I add a mass to it or whatever. Okay, force normal, the desk pushing up on the block is also affected by what things that we do have up here.
Gravity.
Okay, the value of little g is going to affect normal force. That's right. Okay, what else? Okay, force applied, absolutely. If I go up here and I push down on this or pull up on it, it's going to change the normal force. Okay, and the mass as well. All right, the mass of the object. So these three things affect normal force, which then affect force friction. Okay, so they indirectly are the correct answer. All right, next thing that affects friction is the surfaces that we have, or the material. All right, we just said. Okay, so what kind of materials are we talking about? We talking about wood? We talking about like some kind of metal? All right, are the surfaces like, are they wet? Okay, are they like oiled surfaces or something like that? Okay, the materials. All right, so we have that up here. And scientists decided that we can't call it that. All right, we got to call it something much more sophisticated. Okay, and they came up with this term, the coefficient of friction. All right, put that into your vocabulary. Throw those words around in the hallway with your friends. Okay, that's fun to say. All right, coefficient of friction. And we're going to talk a lot about this today. Okay, this is kind of a cool thing that we get to learn today, coefficient of friction. All right, now we already know how to figure out the value of this numerically from last time, okay? But we don't know about this. I'm gonna show you some examples here of various coefficients of friction. Okay, and this slide's a little bit hard to see, so we'll turn the lights off. And I write down some of these. Before I show you some of the examples, let's go over symbols a little bit. Okay, so how do I abbreviate force of gravity?
mg.
All right, mg or fg. How do I abbreviate normal force? Fn. Okay, now how do I abbreviate coefficient of friction? All right, it is typed up there for you. Practice writing it. It's kind of a cursive lowercase u. It is the Greek letter mu. All right, like so, mu. That's the symbol. That's the symbol we use for coefficient of friction. It's a Greek lowercase letter. You'll get good at writing it. Okay, so examples of mu values or coefficient of friction. some low friction examples, okay, our shoulder joints and our hip joints, all right? We got a ball socket, all right, and inside that socket we've got a smooth bone here, okay, and then the inside, and then what's this filled with right here? Ewy stuff. Yeah, like cartilage and fluids and biology, all right? Gotta go ask Mr. Hoisington about that. Okay, and we don't want a lot of friction in our joints. Okay, so the mu value for your shoulder is about 0.01. I would write down a couple of these examples so that you kind of know the range of mu values. Okay, question?
So like arthritis affect the friction in your joints?
I don't know really. It could. I know if you got like bone spurs in there or something like that. Okay, that's gonna make it kind of grind a little bit. But I don't know if arthritis affects the mu value. It's a good question. Similarly, do we want a lot of friction in wheel bearings? No, we want these things to roll and slide really nicely. This is some skateboard bearings, but it doesn't matter if it's a trailer, a car, whatever. All right, mu values are really low in bearings, in wheels. Okay? All right, cars sliding on the road. A Mr. Hicks driving safety lesson for you guys. Okay? Turns out we want high friction values when we're talking about cars and concrete or asphalt. Okay, so if we have a wet road, the coefficient of friction, this symbol, mu, all right, wet road, mu might be about 0.6 depending on where you look it up. Okay, different internet sites will say different things, all right, and that's because these mu values are determined experimentally. Okay, all right, dry road, any guesses? Well, first of all, higher or lower mu values? Okay, higher mu values. So dry road, it's going to go up to about 0.85. All right, this road is going to stop you more quickly. Okay, we could also talk about the brakes and stuff like that. We'll do that in a second. And I have now given you guys 4 examples of mu values. Okay, all right. Does anybody have any kind of problems with what I have on the screen?
Is there like a max? Like it only goes to a certain value?
Okay, that's a good question. All right, you are going to find that most mu values are less than 1. Okay, so you're going to see a lot of small numbers up here. That's true. Okay, what else?
When would the mu ever be above like 1?
I'll show you in a second because I'm going to show you a big table with lots of them. All right, you can have mu values higher than 1. All right, it does happen, but most of them are going to be less than 1. Okay, anybody notice anything about right here, right here?
Big difference.
It is a unitless value. Okay, yeah, they are. Yeah, there's a pretty big difference there. Okay, we're always hammering on units. Okay, put your units on. Make sure the units are correct. Okay, this is a case where we have a unitless value. Okay, mu is actually a ratio of 2 forces you're going to learn when we learn the equation. So we'll go into why it's unitless when we get a little bit more mathematical with this. Okay. Another thing that you have learned already that is unitless is pi, okay? Because pi is a ratio of circumference divided by what? Okay, divided by the diameter of the circle, right? You've got a circumference divided by a diameter, okay, that's pi. And when you divide a unit by itself, you get a unitless quantity. Okay, so like pi, mu has no units. Okay, more mu's. Let's check this out. Okay, we can pull up you can look this up on all kinds of tables. I just pulled one up called the Engineering Toolbox. And here's a chart of mu values. So we've got all kinds of materials. Yeah, we got all kinds of materials, all right. this sliding on this is what it means. This sliding across this. Okay, then we got conditions. Okay, is it clean? Is it dry? Is it oily? All right, is it wet? Temperature can be a factor. Okay, and then over here, we're not really going to talk about this yet. Static versus kinetic, we're going to kind of ignore that for a minute. We will get to that today. Okay, so some interesting things. Let's check it out. We all got to stop when we're in our car's brakes. So we've got brake material sliding across what's in your wheels, okay, which is basically iron, steel, okay? And there's a difference here, okay? If your brakes are clean and dry, all right, we've got a mu of 0.4. All right, if they're wet, mu goes down to 0.2. It is harder for your car to stop you when your brakes are wet. Okay, do they get wet when you're driving? Do we have water in our brakes? There's no way to keep those dry. Okay, so if it's raining, you have wet brakes. All right, not as efficient as stopping you. Okay, anybody see anything else interesting on here? Aluminum on aluminum, pretty high mu value, huh? Okay, all right, let's take a look at some more. It's a whole table. You can look up all kinds of things on this. Okay, we got diamonds on there. Okay, here's an interesting one. Let's take a look at this. All right, glass sliding across glass. All right, these are two very smooth things. So we might think, okay, or at least I thought when I first learned this, oh, those would slide really easy. They're very smooth. Okay, however, if you think really small, a plate of glass, all right, if you were to zoom in on it like with a microscope, a plate of glass will actually lock together really well with another plate of glass. Okay, so pretty high mu value.
Is that like because it has little almost spines? Because I know that's how carbon works.
Yeah, the
Carbon
little
has
pores.
spines.
Yep, lock together really, really well. Yep. Okay, other stuff. Let's see. What else can we look at here? We got ice sliding across ice. And of course, we're Coloradoans, so we better go down and talk about skis. Okay, let's check this out. All right, this comes at a perfect time. We're talking about the physics of skiing. Okay, so the snow conditions, all right, wet, dry, or dry and very cold. Okay, we're going to have higher mu values for wet snow than dry snow. Okay, so spring snow, you know, we're up at Powderhorn, it's kind of sticky. You go slower. Okay, cold winter, dry snow. All right, mu value goes down. And then this is all for wax skis. What's with this -10? Why does the mu value go up? I don't know what's going on with that. Dry, -10. This last one doesn't make sense to me. Okay. All right, what else we got here? Oh, okay, what about inside of our car? Okay, where does steel slide across steel? Well, let's look at these two. Okay, inside your engine, that's right. Okay, all right, so we're always talking about car maintenance, like, okay, you gotta have oil changes every 3,000 miles or whatever. Okay, if, let's say the pistons, all right, are inside the cylinders and there is no oil in it, okay, clean, dry pistons, okay, look how high these mu values are. All right, look at that. Okay, the mu values go down significantly because we put oil in our engines. All right, if it all drains out, you're going to create a bunch of heat. All right, you're gonna ruin your engine. Okay. All right. So how are these determined? Okay, how did scientists get these? Okay, testing. They're experimentally tested, and so you're going to do a lab where you find the mu value of your shoe on the floor. Okay. And all you have to do is take a spring scale and measure the force it takes to drag your shoe across the surface. Okay? And by knowing how hard you have to pull, and this value right here for normal force, you can figure out mu values. All right? So they're all done. done experimentally. The police can figure out the friction of the road with tires by taking a piece of a tire and a weight and dragging it across the road. Okay, they can figure out the frictional value and measure skid lengths and figure out like if you were speeding, stuff like that. Physics cops, right? All right, question?
I know that you were concerns here, but so how, like, as it increased, like, how, what, from -10 Celsius to -80 Celsius?
Yeah, that skiing one.
Yeah, I also saw it up more, where it went from 0 to -11, and it also did the same thing. I don't know. I knew.
But with a different material?
Yeah.
Yeah, I'm gonna have to study that a little bit more. I don't know what the deal was with the -10 and the friction going up. Okay, adding to our notes, 2 types of friction. We got static and kinetic. Okay, let's write these definitions down. Okay, static friction. All right, if I come up to this and I apply 2 newtons of force on my spring scale, okay, this is a force applied. All right, why is it not moving? Why is it not budging?
Not enough force.
Okay, not enough force to overcome static friction. Okay, so if I do 2 newtons, static friction will pull back with 2 newtons. Okay, if I use 4 newtons, static friction's still holding it in place. All right, 4 newtons that way. If you were to do an FBD, 4 newtons here, 4 newtons for static friction. Okay, it will simply match me until I overcome static friction, and now we're into kinetic friction. All right, it is sliding. Okay, now we got to be careful with that. We will learn later that static friction can act on moving objects. All right, we're not going to deal with that right now. Okay, but we can have static friction on moving objects. Okay, and you also might notice, all right, sometimes it is harder to budge something than to keep it moving. Okay, so once you break free of static friction, most of the time your kinetic friction is going to go down. All right, it's going to be less newtons when it's moving than it is to overcome static friction. Okay, and we'll do that kind of in part 2. Okay, so how to calculate friction. I present to you the fun equation. All right, this is the static friction equation. And the symbols, Fs, that's force of static friction. Mu static, we put a little s down there to say we're talking about static friction. And then we can use N or Fn. All right, most of the time I use Fn, but I use capital N here because it's the fun equation. All right, this calculates the maximum static friction. And we'll do some, why is it just the maximum? We'll do some stuff with that kind of in part 2 as well. Okay? All right. If the thing is sliding across another surface, we got kinetic friction, and we just replace everything with K's. All right, we'll do some example problems with that in a second that have to do with skiing. Okay? And a couple things to think about here. Okay, ice versus the road versus the normal road. What in this equation is being affected?
The mu.
Mu value. Okay, we could look it up. Icy road versus dry road. Okay, trucks in the winter. All right, they don't do so well when they are empty. Okay, because we are lacking what in this equation? Okay, we are lacking normal force. All right, so some people might put some weight in the back, maybe some sandbags, all right, or maybe you just have stuff in the back of your truck. That is going to increase the gravitational force on the truck, thus increasing force normal, and then you are going to have more friction back here. Okay, turns out, by the way, we want static friction. All right, preview to next time. Okay, if your tires are spinning on ice, what kind of friction do we have? Static or kinetic? Kinetic, okay. But if your tires are rolling but not sliding across the surface, then we've got static friction, all right? Hence, we'll have a moving thing, all right, but static friction between the tires and the road. Okay, here's changing the mu value by changing your tires. Winter snow tires are made out of a different kind of rubber that have a better mu value on ice. What's being affected here? Again, mu value, it's a wet road. Here's one of my police friends. I won't say his name because we're putting this on YouTube, but the cops get to practice with this kind of thing. How fun is that? Just big kids playing with toys. Kind of like the fire department. Oh, great video here. Okay, all right. This video is called Best Man. All right. How many of you aspire to be a best man in a wedding someday? Yeah, good goal. Okay, now if you are the best man, you have one job. What is that job?
Make your friend look
Give
good.
the vows.
No, not to give the vows.
The ring.
Your job is to hand the ring to the groom.
Yes. That was my
Yeah.
second try.
Yep. Okay, and then you got to give a speech too.
I would be.
But at the wedding, all you do is you take the ring out of your pocket, you hand it over. That's all you do. This is the biggest epic best man fail right here.
Have you ever been a best man?
Will you
have
have
the best
Keith
man.
to be your wedding husband,
Did you
to live together
Good
in the
speech.
covenants of marriage?
Did everyone
Will you
clap?
love him, comfort him, honor and keep him, in sickness and in health? And forsaking all others, be faithful to him as long as you both shall live. The rings, please. Oh, God! No!
Into the pool she goes. Oh, I love that video.
Wait, if I thought